Okay, what we're going to do here is another problem. This is going to be, I suppose, part 4 by now of the review for the Chapter 3 test. And we're talking about non-horizontal projectile motion here. So let's do a problem where we have something. Wow, look at that. Start off real smooth. Let's say this is the ground. I'm trying to draw it level here. Let's say we have something being launched at some angle. Let's say, for example, this is going to be 20 degrees. And let's say we're launching at a speed or velocity here, in this case, of 50 meters per second. And it's going to go like that. It's going to go into the air, and it's going to make this kind of a trajectory, and it's going to come back down, and it's going to land right there. That's the landing spot. Okay? And I'm going to ask a couple of questions now. The first question I'm going to ask is for you to take this initial velocity vector here, 50 meters per second at an angle of 20, and resolve this into its vertical and horizontal components. So by now you should be able to take this and give me the initial velocity in the x direction and the initial velocity in the y direction. So let me say pause it and see what you can do, see what you can come up with. Alright, so what we should have come up with for this first part, where I would ask you for the components, is you should have recognized that if you drew a little, well, let's say, I'll tell you what, let's do it in I don't know why I'm choosing this color, but let's say if I draw a little axis right there. It's supposed to be straight, but you know how it is. Alright, so initially we want to find components, okay? So let's do that. This guy right here is going to be my x component velocity, v sub x. This guy right here is going to be my y component velocity. So by now you should know how to calculate v sub x and v sub y given any vector at any angle. And so v sub x, you should have figured out, is going to be 50, the magnitude of this launch vector, 50, times the cosine of 20 degrees. And this y component over here is going to be 50 times the sine of 20 degrees. So the x component should be, according to my calculator, 46.9, so we could roughly say 47 meters per second. And the y component should be 17.1. And if I'm wrong, you guys correct me, all right? But anyway, 50 sine 20 should be 17.1. 50 cosine 20 should be 46.9. So that was the first thing you needed to do. Now the next thing I'll ask you is, how long is this ball, or whatever is being launched over here, and it's going way there until it hits this x spot here. How long is it actually in the air? How can we do that? All right, well, there's two ways we can do that. The first is to recognize, and we're going to consider, in order to find time, so to find time in air, we're going to have to consider the vertical information. And there's two ways we can do it. Let me show you the first way. First way, we know this formula, delta y, is equal to the initial velocity in the y times time, plus the 1/2 acceleration in the y times time squared. And we want to consider where the delta y is actually equal to 0. Why do I say that? Well, I want to know the time right here. Well, right here at that position, notice that the change in y is 0. It goes up so many meters, and it comes down, and it's back where it started from as far as vertical is concerned. If it starts on the ground and it ends on the ground, then vertically it went nowhere. So its displacement is 0. Does everybody see that? It starts on the ground here ends on the ground. As far as vertical is concerned, my starting position and my finishing position is the ground. So it did not go anywhere or displace itself in the vertical or y direction. So this is key. I want to know where the change in y or the displacement is 0. In other words, I want to know where the starting and the finishing position is the same when it hits the ground. Now, the initial velocity in the y direction is initial. That's where it starts. Well, in this case, it's not going to be 0. The initial velocity, we said, is 17.1. So let's put that in, 17.1 times the time. That's what we're trying to figure out. We don't know that. Plus 1/2, what's the acceleration? Negative 9.8 t squared. So let's look at this algebraic equation. 0 then is equal to 17.1 t minus 4.9 t squared, because half of 9.8 is 4.9. And now if I factor out t, I got 17.1 minus 4.9 t, because I got a t here and I've got a t squared here, so I pull out a t. And now in order to solve anything, any two factors equal to 0, I said each one equal to 0. The one I'm interested in is this one right here. So I'm going to look at 17.1 minus 4.9t, this guy here. Let's set that equal to 0, and if I do, I'll find time is going to be equal to 3.49 seconds. The other way I could find time is to consider, so here's the other way I'm going to find time, is to consider the final velocity in the y, let's call it v final in the y, is always going to be equal to the initial velocity in the y plus acceleration in the y times t. So v final equals v initial plus at. Final equals initial plus at, talking about the y direction. When I have something that goes up and comes back down to its initial starting position, whether I throw a ball up in the air and I catch it at the same level or something else, it doesn't matter. The thing to remember is that the speed, magnitude-wise, that the thing is going straight up from at launch is going to be equal to the speed it's going to come back down at when it hits where it started from. I think I just confused you. But basically what we're saying is if I take a ball, right, at this level and I shoot the ball up in the air and I launch it at 5 meters per second and it goes straight up, and it stops and it comes back down again and it hits that same spot, it's going to hit it at 5 meters per second down. So if it goes up at 5 meters per second, when it comes back down at the same spot, it's going to be 5 meters per second, just the opposite direction. And that's what happens when you have vertical, consider the vertical motion piece. So if I have, in this case, something going up here at some initial velocity in the y direction, it doesn't matter. The x direction is independent. Over here, it's going to come back down. The final velocity is going to come back down. This guy in magnitude is going to be the same as this guy. It's just going to have a different direction. So the final velocity is going to be equal to the initial velocity plus acceleration times the time. Well, what's the initial velocity? The initial velocity here is what we calculated right here. That's 17.1. And it's plus, because it's going upward. What's the acceleration? Negative 9.8. We don't know time. If we know the initial launch here is 17.1, then the final is going to be 17.1, but the opposite direction. It's going to be down because the final over here is down at 17.1. See, if it goes up at 17.1, it's going to come down at 17.1 at the same level location. When I do this and try and solve that, what we're going to have, we're going to find that t is going to be also equal to 3.49 seconds. So either way, you can solve that. Either think of the position where delta y is 0 and then you factor out and you solve for t, or you recognize that the final and the initial component in the y direction are magnitude going to be the same, but directions are going to be different, and you can solve for time in that fashion. So that's how we solve for the time in the air. The other thing we might want to know is the range of the ball. So what's the range? The range is how far, here's the range up here, range is how far it travels in the x direction. Range is sometimes going to be called this delta x. It's this position from here, from where we started. That's the range. So the range, put it up here, range, we're going to look at delta x, and that's going to be the initial velocity in the x times time, because this is the horizontal equation that we use for projectile motion. So delta x is going to be the initial velocity in the x, which we calculated at the start as 46.9 times the time, let me put times this way, times the time, which is 3.49 seconds. And if we do that, we've got ourselves a range of 163.7 meters. All right? So that's about all I really want to do as far as this kind of a problem is concerned. We need to know how to separate into components, x components and y components. We need to know that that's initial. We need to know the final occurs where it hits. We need to know what the range is. That's the delta x. We need to know this delta x formula here. We need to know how to find the time in the air, and you could do it of one of two methods. This is method 1, this is method 2, whichever you like best. All right. This is easier probably to remember because once you calculate the initial velocity in the y direction, you know if it's shooting upward, it's plus. So this is initial, there's your plus. The final is going to be the same magnitude, but it's going to have the minus sign. And then when you solve this, because you'd have minus 17.1 minus another 17.1 equals minus 9.8 t, you combine these two and then you divide by negative 9.8 to get your t, and that's going to be in seconds. Well, I hope that helped, and we'll catch you later.